Okay, so I want to say some more things about the Heyting algebra and some sort of related ideas. So, one of them is this interesting idea of the implies arrow as an exponential object. So, I mean, here I'm thinking in particular of sub A. Okay, so this is the category which has sub-objects of A as the objects and an arrow from one object to another when the first is included in the second. And this is a Cartesian closed category, and the exponential object is this object x implies y, which is basically as a sort of like in set, for example, it's the set of elements which whenever they're in X, they're also in Y. So something like what I've shown with this yellow shading here. Now, the interesting thing is that this is an exponential object. So somehow we can think of this kind of subset as representing how X is contained in Y. And in fact, we see that this actually just has, well, it has a point 1 precisely when X is contained in Y. So we see this because it's an exponential object. So just using this kind of property means we can put this X downstairs like so. So in general, S is contained in X implies Y if and only if S intersection X is contained in Y. So for example, this is this subset S is such that S intersection X is contained in Y, and therefore S is contained in this yellow subset X implies Y. Now when we take this S to be 1, as in we take it to be, 1 here is a terminal object, but it corresponds to the maximal subobject. Well, that would correspond to saying then that 1 is contained in X implies Y. In other words, that would be a situation where this yellow shaded region would fill the entire space up. So that would correspond to a situation where X is contained in Y. And this is exactly what we get from the exponential object algebra as well. If we have S as 1, and we see that what this means is that 1, there's an arrow from a terminal object to Y to the power of X, if and only if there's an arrow from X to Y. Because this is a pre-order, okay? And Y to the power of X is X implies Y. And so that corresponds to this kind of relationship that 1 is contained in X implies Y if and only if X is contained in Y. Also, I was thinking about what the evaluation arrow looks like. So it is in fact true that there's an arrow from Y to the power of X times X to Y. This is the evaluation arrow. So we have this. Why do we have it? Well, we obviously have that X implies Y is contained in X implies Y. And now if we just use this sort of relationship, this means that we can replace this X implies Y on the right with a Y, and we can stick an X on the left with an intersection, and we get this formula here, okay? So the main thing I want to show, and this is sort of, well, I'm not exactly going to prove it because it relies on some extra results but I'm going to make an argument for most of it, is another way of talking about ore. Okay, so remember, Goldblatt defines. Well, I'll go through how Goldblatt defines ore. Well, basically, he defines ore to be the classifying arrow of the image of this arrow here. Now, another result that he gives is then that if we have a couple of monics, well, a couple of subobjects F and G of D, then we have the F union G is equal to the image of this product arrow, F comma G. So we can see this here, like if we have these two subobjects of our graph, and we have, well, shown by these two things of green arrows, then if we sort of take both at the same time, so we've got F comma G, so we sort of think of this now as a co-product, and sending both of these arrows in, and then we take the image of them, then that sweeps out this this sort of region which contains stuff from both of them, and this is the union of F. This is a union of F and G, which we might also call the subobject classified by or of chi F, comma chi G. Okay, so we'll get on to that. I just wanted to say a couple of other things. One of them is just some very kind of, well, quite some observations about what this slice category looks like, because sub A is really a subcategory. It's a full subcategory of E slice A. And so how are we to think of it? Well, the objects of E slice A are arrows into A. And so sub A is that kind of thing, but just considering the monics which are going into A. So when you think of those as like specially highlighted, specially kind of highlighted objects in this slice category, and what kind of functions do they play? Well, what kind of roles do these monic objects play in this slice category? Well, they are these other kinds of arrows, like for these blue ones that are just regular arrows into A, some of those are going to be in these different monics. And so we can think of these sort of special objects as like housing these other objects. So these sort of sub-objects, these monics into A are sort of housing the other arrows. And more than that, we can ask for a particular arrow. Well, what's the kind of minimal, in quotes, monic that is contained in? And that, I think, is going to be the image. So, for example, the image of P is going to be the minimal kind of subobject of A, which P is in. And when one considers this in conjunction with, the fact that we have all this lovely logic about these subobjects, and we can do this kind of f to the -1 functor to go from one of these one of these kind of sub-object categories to another. I mean, it begs questions like, how do we extend those kind of functors to work over the whole slice category? Maybe we can just do pullbacks of everything. So yeah. And there's various other nice relationships. For example, I think in round about page 144 in Johnston, he mentions that the existential quantifier is an adjoint to this functor f to the minus 1, which sends our category of subobjects of B to this category of subobjects of A. Anyway, another thing to say about this relationship, remember in this slice category, we can think about these fibers. And so if you're looking at the fibers, of an arrow Q over some element Z of A, or if you look over all the elements Z of A, I mean, say we're dealing in sets, you find all the non-empty fibers, then if you just replace each of those fibers with a single element, then I think you get the image of that Q. So that's sort of a way you can relate the fibers with these kind of images, these kind of minimal sub-objects that the things live in. Something just briefly to say about internal versus external. Often when topos theorists are talking about things being internal, like internal logic, etc., they're talking about stuff that happens to do with omega to the power of A, because that's like an actual object of the category E. So it's something that in some sense is like visible to a topos dweller, whereas external semantics is usually, or external logic is talking about sub A, because this is a sort of category, a pre-order that we form externally and think about. Okay, so on with this result then. Firstly, a lemma. If we have a pullback like this, so we have arrows V and F and arrows G and U, then if we do the epimono factorizations, for example, we factorize F into, we write it as IMF after F hash, and we write G as IMG after G hash, then our claim is that, so remember this F with square brackets of A, this is the domain of the image of F, and similarly this with G. So the claim then is that given a pullback like this, where we have this pullback of an arrow G from C to D and an arrow V from B to D, given by U from A to C and F from A to B, then the claim is that there's an arrow H from F of A to G of C that makes the right square of this commute. So basically what this is saying is that when we have a pullback, we can replace two of the kind of parallel arrows in that pullback square with their images, and we get another pullback square. Okay. I mean, we'd also have to replace one of these two arrows going in the opposite direction. The one that's not involved in the pullback diagram. So here's the proof then. We consider this type of diagram, and we suppose that the right square here is a pullback square. So what have we got in here? Well, we've just got IMG. We'll just think about this right square for a start. So we've still got IMG from our original diagram, and we've still got V. But this other stuff is potentially new. Okay, so we suppose this right square is a pullback. So in other words, I is the pullback of IMG along V. Well, that means I has to be monic. So we have that for a start. Because it's a pullback of a monic. Okay. Now, secondly, we'll think about the rest of this diagram now. So suppose we have this arrow F drawn in, and these arrows U and G hash. So we know that these two composed are going to give G. And we know that VF is equal to GU. We know that because we're assuming that up here, okay? And just expanding this out, we get that VF is IMG G hash. So then we have that these two things, F and G hash after U, are sort of pullback candidates. So there has to exist this unique arrow F dash from A to E, which is such that H dash after F dash equals G hash U, and I after F dash equals F. So that means that this whole diagram has to commute. Now, our assumption originally is that this is a pullback. GU VF. So that means that the outer perimeter of this diagram is a pullback. And we're also assuming that this right square is a pullback. So the pullback lemma implies that this left square is a pullback. And one of the results, there's a couple of results I'm going to refer to today, which are sort of normally thought of as consequences of the fundamental theorem of topos theory. And I'm not going to prove those. I'm just going to sort of state them as axioms or whatever. So one of them is that the pullback of an epic is an epic. So that means that F dash here is an epic. So we have that F dash is an epic. And now the thing is that what we have is that a monic followed by an epic composed together give F. So we can think of I after F dash as a sort of epimonofactorization of F. Now, epimonofactorizations are the epimonofactorization of an arrow in a topos is unique up to isomorphism. So essentially this is sort of solving our problem, because our goal is basically to show that this right square is a pullback here. But it's not quite that simple. It's nearly that simple. So what we can really say, this is from sort of Goldblatt really, is that an epimonofactorization of, we have an epimonofactorization of f. So we have this unique k, which is an isomorphism from E to f of a, such that this triangle commutes. So we've shown that this is a pullback. And so using that triangle, we can define H to be H dash after F dash. And that diagram above gives us I after K to the minus 1 is IMF. I after K to the minus 1 is IMF. And then since this K to the minus 1 is an isomorphism, which also sort of acts like an intermediary arrow, it follows that the outer square of this is a pullback, and that's what we wanted to show. So okay, that's one of the lemmas that we're going to be using. Basically, this lemma that when we have a pullback square, we also have this kind of pullback square involving the images. And now we can go for our main result. So we just recall then that Goldblatt defines OR as the classifying arrow of the image of this arrow, true, 1, 1, true. An image, I mean, Goldblatt discusses how you can construct the image as the equalizer of the kind of canonical injections involved at the push out of F along itself. Another way you can think of it is using Lever's definition. So given an arrow, I think this is correct. Given an arrow F from A to B, the image is a subobject of B such that F is in it. And if J is a subobject of B, and F is in J, then IMF is in J. So we think of it as a kind of minimal subobject of B that contains F. So now this is our main result that we want to get at in this video, which is that if we have the subobjects F and G of D, then this arrow, which is the image of F comma G, this product arrow here, has a classifying arrow which is OR of chi of F comma chi of G. Or in other words, simply we have F union G is the image of this product arrow F comma G. So I did a picture of this before. Way up here. Yeah. Okay. So the proof then. Firstly, we want to show that the small squares in this diagram are pullbacks. Okay, so if you look at the picture, you'll see that there's a lot of symmetry here, and it suffices just to show that one of these squares is a pullback. So I'll do it for the left square. So if we consider this square, we have, firstly, we want to show that the square commutes. So composing along the top right, we get chi of f after f, chi of g after f. We know that that first one's going to be true A, and the second one's going to be chi of g after f. And then composing this way, we get t exclamation mark omega after chi g of f and chi g of f. Well, this t of exclamation mark omega chi g of f is just going to be t of a. So these are equal. So this is a commuting square at least. But we want to show that it's a pullback. So now let's suppose that we have this object V with arrows alpha and beta, such that t omega comma 1 omega after alpha equals chi f comma chi g after beta. So given that those two things are equal, they're equal component wise, and so we're going to have that chi of f after beta equals tv, and chi of g after beta is equal to alpha. So this left one means that beta is in f, and so there exists a unique k such that beta equals fk. And so as an intermediary arrow, we have to have this k up here. And then does it also make this work? Yes, it does, because composing these, we get chi of g, chi g fk. Well, what's chi g fk? Well, we know fk is beta. So this is going to be chi g of beta. But we know that chi g of beta is alpha. And so this makes this left triangle commute as well. So this works too. So there we have our unique arrow. So this is a pullback as required. So we have that this left square is a pullback. Similar argument shows that this right square is a pullback. Another one of these kind of should be post fundamental theorem of topos theory facts that Goldblatt states is that co-products preserve pullbacks. So given that these two things are pullbacks, we can kind of take the co-products of the stuff on the far left and the stuff on the far right and get this, which also must be a pullback. So notice what we've done here to get this is we've added together the thing on the stuff on the far left and the stuff on the far right, and changed these arrows pointing into the middle to be co-product arrows. So we have that this is a pullback square by that sort of fact. And you can see this in Goldblatt 5.3 with some references to where you can find a proof of it. Now what we can do is invoke our lemma, so we can then consider the images here. So we then get, what we've done here is we've replaced this top and bottom arrow with images now, using this lemma that I just showed. And so this is also a pullback square. And now notice that this thing on the bottom the classifying arrow of this monic on the bottom is OR. Okay, so what we actually have now, we can put this extra kind of pullback square on the bottom here, which is really just giving us the definition of OR. Okay, because the definition of the image of t comma 1 t omega comma 1 omega 1 omega comma t omega, the image of, if we get the image of that like this, if we get this is a monic, a subobject of omega times omega, its classifying arrow, so let's call that arrow I anyway, so the classifying arrow of I, chi of I, is exactly what OR is by definition. And so we have that this bottom square is a pullback, and we've been arguing that this top square is a pullback. And so then the pullback lemma gives us that the outer rectangle is a pullback. And this is exactly what we want, because the definition of a subobject classifier says that for any monic, like this one, Im of f comma g, there's a unique arrow from its codomain to the subobject classifier, such that this monic is the pullback of true along this classifying arrow, which in our case is OR after chi of f comma chi of g. So in conclusion, OR of chi f comma chi g is the classifying arrow of Im of f comma g. So in other words, I mean, since we have sort of by the definition of union, or at least this is one way we can define union, we can say that F union G is the subobject classified by chi f comma chi g. We've shown that F union G is Im f comma g, which is as we've claimed.